to illustrate the role of the purrs and cries. And so what we have here are BMAL and clock, which are the positive activators of actually a set of at least 5 genes. All 3 PERP genes and both cryptochrome genes appear to be under the regulation of clock based on genetic experiments. And these are activators of all of these proteins. To simplify the animation, we've reduced it to just period and cryptochrome. And as we saw in Drosophila, what happens is once the period and cryptochrome genes are turned on, their RNAs accumulate, proteins are made, but in this case, a number of different dimer combinations can be formed. Per-per dimers, cryptochrome per dimers, and different combinations of the various per and cryptochrome proteins. They then translocate into the nucleus where they interact directly with clock and BMAL to then turn off the period and cryptochrome genes. Then as time progresses, these negative factors, per and cryptochrome, turn over and disappear or degraded. And then the inhibition is relieved, the activation begins, and the start of the cycle begins again. So in the next animation, we're just going to add casein kinase 1 here as a new member of this clock gene family. And as we saw before, we have clock and BMAL regulating per and cryptochrome, and casein kinase 1 will start with its role in the cytoplasm, which we believe is very similar to what has been found in Drosophila, and that is to phosphorylate the PER protein and make it less stable so that it degrades unless the PER forms a dimer with either itself or cryptochrome. Another role that's been identified in mammals is that casein kinase 1 epsilon may also be involved in either cellular retention or translocation into the nucleus. It's a second role. A third role is that casein kinase is also involved in the turnover of the inhibitory complex in the nucleus, as Michael Rosbash illustrated. Once those inhibitory molecules degrade, the cycle starts over, and we see the beginning of a new cycle. Now, if I could go back to the next slide. This shows you a wild type as compared to a mutant hamster in this case. And what we see is the PER genes are produced, but because the mutant enzyme is less effective in phosphorylating PER, we would suggest that PER can accumulate faster in the cytoplasm, then translocate into the nucleus earlier, which leads to an earlier shutoff. The negative feedback occurs earlier as compared to wild type. Now, this is in contrast to the actual example that Michael showed, where the casein kinase effect was primarily in the nucleus. So we think the tau mutation is working primarily in the cytoplasmic location, and we're getting opposite effects of period.